Hi, everybody. Welcome to the Quality Inspection Solutions breakout. We will begin shortly in a couple of minutes. I can see that there are some people joining, so we'll wait a couple of minutes more and then we will start. Okay, so let's begin. So it seems that there's not more people joining now. This is the second session we are doing about quality inspection solutions. First session was done in the morning for European region. There was some 25 people joining. There were some questions also at the end. I will explain briefly about how this session is conducted. Let me go for this uh, first slide. Wait a second. Okay, wait a second. We are here. So, taking a look to that, I will start with a short introduction about myself, about ABB, and about the 3D quality inspection solutions. Afterwards, I will talk briefly about the electric vehicles background, just to have a glimpse of the situation with electric vehicles. They are growing, they are expanding. Um, After that, some points about battery box quality inspection, why it's important, what type of defects are typically checked, and finally, I will go to the ABB quality inspection solution portfolio, offline and inline solutions. Also important to mention, in order to have a fruitful discussion, I suggest that you use by the end, we'll have a Q&A session and you can use the chat to put your questions in advance. So the more questions, the more fun. Second, by the end of the meeting, there will be also a Q&R code. So with your mobile phone, you can scan it and give your feedback about the session. Okay. So guys, let's go ahead. So my name, as introduction, my name is Tony Roda. As I said, I'm Global Product Manager for Vision Products in ABB Robotics. I joined ABB some years ago, so back in 2003. Most of this time, I have been working in the automotive team and more specifically in press automation. Additionally, I have covered several roles in the organization, also in customer service, as product manager initially for press automation, and in this last phase as vision product manager. I will go directly to the topic, EV's background. So, so as all of you may know, electric vehicles sales are growing. Since I remember back in 2008, more or less, I saw the first 2008, 2009 maybe. I saw the first Tesla, but that time there was also the Toyota Prius, which was a hybrid model. After that, we could see that now Renault, PSA, GM, uh, Volvo, all car brands are moving towards the electric vehicles. In fact, Volvo is planning to move 100% electric, if I'm not wrong, by 2030. In that sense, we can say that by 2030, electric vehicles will mean a kind 30% of the total vehicle market. Of course, that depends on the region. That's a global figure, but that depends on the region. In some areas, like in China, that will rise up to 50%, while in Europe and US, it will be moving between 30 and 40%. If we are going to the right-hand side image, we can see that, of course, that we are going still to have internal combustion engine vehicles, but hybrid vehicles or full electric vehicles will grow consistently until this 30% that I mentioned before. Why and how can it be that electric vehicles are growing so fast? Number one, I'd say because of the technology improvement. So nowadays, batteries are improving. Efficiency on the electric motors is way better than it was before. Second, and it goes together, I'd say that there are some regulatory incentives for the users to acquire electric vehicles. For instance, here in Europe, I'm sitting in Barcelona, by the way. When you're changing your internal combustion engine vehicle by an electric vehicle, you have some support from the government. You are paying less taxes. And third, sorry, the increment on the charging infrastructure. So if you have electric vehicle and you can just charge it at home, that's a bad business. But now we can see that there are more charging stations in shopping malls, for instance, or in public areas. You could see that this is happening at the global level. So uh, all that said, let's go up. Let's move to the next one. So electric battery tray and quality inspection. So in the last years, given that electric vehicles have different needs and different uh, structure, so we have seen that the traditional vehicle chassis has changed quite a lot. We are replacing the space for the gas tank. We are also replacing the big um, engine. Nowadays we have different, or in some cases distributed motors. We have also a full battery pack where all the different types of batteries are stored. In this case, there are some topics which are quite important for the passenger safety. We have to avoid the leakages because of the inflammation risk. Also, we need these batteries have to be well protected in case of accident that could happen, an explosion as it happened. And also having quality, it's having quality on the components is important for the battery lifetime. So we don't want to buy an electric vehicle and after 2 years having to replace completely. On top of that, batteries today are still expensive, are an important part of the complete cost. So what are the traditional or the typical quality elements that are being inspected in battery tray? So we have geometrical analysis. At the end, in this case, it's checking the complete battery box dimensions based on a CAD model, if they are reaching the quality standard in terms of size, accuracy. Second, welding seams. These welding seams are conceived to have internal divisions between the different types of battery boxes. It's important to make sure that the quality of that the welding seams are in line with the quality specifications. And third, position verification. Inside the battery box, we have uh, a number of holes, a number of pins, a number of components for the part positioning. So we have to make sure that they are in the right place and they are not having a problem for the later assembly of the batteries. So all that said, we have three quality problems, let's say, and we can go to the quality inspection, ABS quality inspection. I'm trying to go fast. This is just a kind of introduction to spend more time in the ABS portfolio and also to leave some room for the Q&A session. So now I will play a video to better understand how quality inspection is typically done uh, in automotive and using robots. Let me go to the first video, video one. So as you can see here, we have a digitalized part. We are digitalizing with a structured light technology. With the structured light technology, we are throwing a light pattern, as you can see here, to the part. And with the camera and a photogrammetry camera, we are inspecting and checking the dimensions quite accurately and with high detail. This image is going faster than in reality, but you can say that we are inspecting the part. This is the CAD model, that digitalized model that we are taking. You can see that there's plenty of detail. Every point is a cloud point that we are using for later on estimating the dimensions. Depending on the systems, we have more accuracy or less. I will explain later on what is the accuracy of the ABB system. And then, of course, after the digitalization process, we can compare that to the CAD model and having a report of the quality. Right, going back to the presentation. Okay. So what types of quality inspection systems has ABB? Sorry. We have the offline quality inspection and we have the inline quality inspection. Both are typically used in automotive applications, in auto OEM, in tier one, also in other types of general industries. But we'll focus today on the case of the battery tray quality inspection. I will explain later on about in more detail each of these systems, but now uh, as a quick introduction. So if we are talking about the offline quality inspection, we have to think that this is geometrical analysis or metrology, as it has been said for a while. The main the main tool for comparing is having a CAD. We are using a CAD comparison. We are digitalizing a real part. We are comparing to a CAD model, and based on that, we are taking the dimensions on the holes, slots, trim points. We are having a color map or surface points. In that case, the acceptance is related to some rules, some guidelines. It could be MS-A4 or it can be different types of criteria. At the end of the process, when we are comparing the CAD with a digitalized model, we have a report which highlights the differences. So if they are inside the right tolerances, we could say that this part is okay. If not, this part is wrong. Offline is typically used for, let's say, statistical process control. Let's say you are inspecting one part every 2000 or one part per batch or two parts per batch. That depends on the lot size. Then we have 3D quality in line, 3D QI in line. In this case, we are using this type of solution also for geometrical, but also for process quality control. In that case, the tool we are using for comparing is a machine learning process. I will explain during the the breakout session a little bit about what type of machine learning we are using. In this case, for instance, we will focus on the case of the welding seam quality inspection, and the acceptance criterion is based on qualitative aspects that we are using comparing to existing case. In any case, at the end, we have a reporting a report of the process where it will validate if the part is okay or not okay. So as said, we have two types of quality inspection solutions. One is offline, one is inline. In these images, you can see the battery box in both cases, in the offline checking, but also in the inline inspection for the welding seam. Okay, so let's go for the 3D quality offline. Okay, so the AV solution of the quality inspection. Wait a second, please. It seems that there's some background. Can you hear? Wait a second. Sorry, there was some background. So as I was saying, the 3D quality inspection offline, ABB is offering a complete cell solution. We are offering modular concept for cells, different types of cells with several types of turning tables, different robots. In this case, this is quite interesting because you can deliver a fully proven solution to the customer. Even we can do the testing at ABB premises and deliver the complete cell. This is the closest we can think about a plug and play. We understand that we are in an industrial environment and plug and play is not exactly the same as what we are doing at home. But in that case, the cell is proven, the cell is working. Even we can check in advance some of the parts that will be inspected later on. Here we have a couple of examples of the modularity concept. As you can see here, we have in the left hand uh, a cell with a single measuring station. You can see that we have a turning table with one robot. On the right hand, we have a cell with two measuring stations. That means that we have two turning tables, but additionally, as in the modular concept, we can have automatic loading of the cells, we can have more robots, we can have more tables, we can have different payloads for the rotating tables. I will go to show a quick video, so you will see how this it works. It seems that the video is not loading. Wait a second. Now, so this is a standard cell by EV. In this case, it have two loading position. You can see that the operator is loading the turning table. In this case, they are using this manual clamping tool, but that can be automated with the standard fixtures. Once the part is inside the cell, the robot will start uh, with the inspection and with these light patterns that the camera is later on acquiring to have a complete digitalization of the part. Depending on the part size, the cycle time will be shorter or greater. That was one question from the previous uh, Q&A. We can say that the typical process for, let's say, in that case was an axle, could be between 4 to 6 minutes. That's much less time than the traditional CMM methods that were taking some hours instead of minutes for the complete part inspection. Sorry. As you can see, once the part has been inspected, the turning table is rotating and the operator can take out this part. In this case, we are doing inspection for in that case, sorry, I will go back to the presentation. In that case, you have seen we were doing inspection of a welded part, but for instance, for let's say stamped parts in the press automation side, we can inspect a complete body side, and that could take this 4 to 6 minutes. Okay. I will show some examples of the typical parts that are being inspected. In this case here, you can see that we were putting together, this is not a 100% standard cell. We're putting two robots on track conveyors because in that case we were analyzing the complete volume of a van. You may understand that the robot needs to go inside. It has to full digitalize the complete van. So it takes more than the 6 minutes I said before. Thanks to the robotics technology, we are flexible enough to go inside the van and to check all the features and all the different parts. We go next. In this case, this is the standard cell that you have seen before. That was for a customer in South Africa. In that case, we were having two loading stations, one in the front, one in the back, with one single robot. Additionally to the geometrical inspection, we're checking the clipping hole position. So we have here another example. In that case, it's just the analysis of stamped parts. In that case, that's a door from a truck company. We are having a kind of open cell concept because of the size of the parts that we were inspecting. In this case, um, being a truck. In that case, we're using just for geometrical inspection, having a complete digitalization of the part and having a report with indicating the quality, if it's red okay, green not okay, based on some parameters previously defined. I'd like also to explain briefly the digitalization process. So sorry because it's late here and my tongue starts to not to be okay. But for instance in this part, this is a V pillar. We are using 4 complete shots to have the complete digitalization of the part. We are considering some 0.3 seconds per shot, depending, of course, on the number of on the quality of the information you want to have. But if you are going deeply, you can see that out of this digitalization, we can have uh, detailed information of this trimming hole. What type of defects or features are we measuring in the offline inspection? Holes, slots, rectangles. You can have X, Y, Z position. You can check the diameter, edge and trim points. So you can also check that. Let's say that we are working on a laser cutting machine. In that case, that could be also traditional V-pillar. After hot stamping is going to a laser machine, so we can check the quality of the trimming process. Surface point. That's the example we have seen of the track door. So we can check this surface point. Wait a second. I'm moving to the next one. Also, we can check distances and angles. This component, this part is the one that we have seen before. In this case, we are checking the distance between uh, parallel faces, between holes. We are checking also the angle and the relative position between them. Also, we can inspect cross sections in order to make sure that the part is okay. And also, we can have a color map. Okay, so this is related to the offline inspection. Of course, that there are more features, there are more processes that can be done. As a summary on the offline, uh, offline means that we are taking one part out of the production flow. We are doing a detailed inspection. Also, before I mention stamped parts, but why not analyzing a complete die to make sure that the die is inside the tolerances. On the opposite, when we are going to the inline, we are targeting 100% of manufactured parts. In this case, of course, that we are faster, we have a faster sensor than in the offline version. This is 0.1 seconds per scan. On the other hand, we have less information from each scan. So what we are proposing here is a function package. The difference between a function package and a cell is that we understand that this type of equipment has to be integrated in the production line. Imagine in that case of the image, you can see the robot with the vision system, which is analyzing and taking images of a welded part. One important point that we have to remember about our product is that this system is able to inspect geometry and process at the same time. What I mean by process is analyzing the quality of a weld, of a welding seam. We can analyze or check a spatter. We can check the riveting. We can check a number of different features. Additionally to that, I said that it was originally conceived to be inline, but also we can use that on a bypass station. At the end, we are taking some parts out of the production cycle, and once they are inspected, they are going back to the production cycle. That's called by the line inspection or bypassed. But also we can integrate this function package, which is mainly composed of the robot with camera, the robot controller, and the software. We can integrate that also in a standard cell. So we have a number of standard components like the safety enclosure, rotating table, the robot stand, also the HMI. And in case that we want to have this bypass station, we can fully supply that 100% tested and validated. In this case, I wanted to highlight this. This is the sensor developed and designed by ABB. I can say that I'm really proud of this sensor. Inside this piece of engineering, there's the know-how of I would say, a brilliant team of engineers that have been working in 3D quality, metrology, quality inspection for some 20 years. So this this sensor, I would say that it's best in class on the inline quality inspection. As I said before, scanning time is 0.1 seconds with a resolution between 12 and 1.4 megapixels on the same sensor. We are having integrated flash, and we are using, in this case, LED illumination, which is reducing the maintenance effort. Additionally, I have to say that this is IP5X protection, so we are not 60, but we are close to that. I will talk briefly also about the software. We are using all these quality inspection solutions are using Polyworks, which is a well-known software for quality analysis. Also important to mention that both inline and offline solutions have plugins and are integrated in our Robot Studio. This is optimum for offline programming, but also for the automatic path planning. Regarding the quality inspection, we have what we call Inspector Suite, which is the user interface on the HMI, which is user-friendly, it's simple, and it's guiding the user through the quality inspection process. And then important to mention is the quality process apps. So we have defined some apps. We are working, for instance, as I said before, on the welding sim analysis, but there are a number of different apps that can be used, like rivet detection, spatter, crater, and some others. In the previous meeting, in the previous session, someone was asking about gluing. This typical glue challenge. At the end, it can be the same. We have some standard apps, some others are not standard, but given the case, we can work on the development of them. I will show a nice video about the inline quality inspection. Let's see. Before it took a while until it was charging. Let me see if now works better. It seems that it's taking a while. So this video is interesting because we're introducing, in this case, the sensor. There are some application cases where we will see one robot with a sensor. I will explain after the video because there's some nice music. I prefer you to take a look at the video. it stopped. So let's go back to the presentation. Okay, so during the video, we have seen that the initial step was the testing in AV facilities with one single robot. We were testing with the customer part. Afterwards, we could see that there was the real case in customer facilities, also with, in this case, with two coordinated robots. Two coordinated robots were used to increase the scanning speed. After that, we have seen that there was a robot studio image where we were able to do the offline programming, also having an estimation of cycle time. And finally, we have seen some images of how the reports and how the information is communicated to the users. Let's go ahead. I will show some existing references, some existing cases. So in that case, this is a quality inspection process in automotive customer. It's one robot which is integrated in the production flow. Before the inspection, there's a welding cell. The robot is putting the part into a fixture. Another robot is inspecting the part. Once it's inspected, then the robot is putting back the part to the production flow. And meanwhile, the robot is already doing the next inspection. In this case, we're inspecting 100% of the parts. We're doing the geometrical inspection of the complete part, as you can see from the report on the left-hand corner. But also we were inspecting the quality of the SIM, if it was inside the parameters requested by the customer. We go to another example. So maybe you remember this part from the offline. This is the, if I'm not wrong, this is the cross-car beam. In that case, we are doing the inline inspection. I would say that in that case, this is by the line cell. So we are taking some parts out of the line and doing a full geometrical inspection. As before I commented about typical defects that we are checking, I would like to go a little bit more on the welding seam inspection. So we are able to check the quality of the welding seams against the qualitative information given by the customer. We can check the length, we can check the continuity, we can check the height, we can check the throat of the welding to see if it's inside the parameters. As you can see, in previous case was in a corner. Also, we can check that on a hole. And again, we are checking the length, continuity, throughout of the different types of welding which are in the part. We have plenty of examples of different weldings that we can find in a typical production and weldings that we have in the battery trays. But it's important here to mention also we can check the geometrical features as we have done before, but how we are giving this information on the quality of the welding to the system. So let's go to that. So on the traditional quality inspection, we have the manufacturing line. In that case, let's say that could be welding. At the end of the line, typically there's the human visual inspection. So the good thing of the human inspection is that they are flexible. If you have good and skilled and trained people, they have a big knowledge on the type of defects that they are looking. Also, it's important to mention that it's really difficult to transfer this know-how to a machine, to a system. It's difficult to put it in numbers because there's some people, I have some cases where there was one guy doing the same work for some years, and he exactly knew by the color of the welding, by the size, the position, he know that if that part was okay or not okay. How then to transfer this information to an automatic, to an intelligent system? In that case, we are using machine learning. So we have an automatic inspection station, which is in the production flow. If we are targeting 100% of the parts, then we are checking a number of different features against some samples that have been pre-trained. How we are training as samples? We are taking 600 to it. We just need 600 to 800 of images of different welding sims that we are checking, and we need to label these defects, saying if they are okay or not okay, and also putting some qualitative information on them. After that, we have a complete database of defects, and we are comparing what the robot is seeing on the new part against this database. It's important to mention that, especially on the initial stages, it's good having human supervision to make sure that the quality is the one that we are looking for. If not, we can retrain and update the model and making the model better. Once the system uh, is trained and validated, what we can do is relying 100% on the system and then sending the defective parts to the repair station or to just making a report for production monitoring. So here you have some examples of the what we call production monitoring. At the end, we can have full detail on the defects, on the features that we are inspecting on each part. That's a typical report. For instance, in this case, we are showing, it's easy to find in this case where the welding seams are and which of them are not correct. So we are indicating for each part which which welding seams have to be double checked if they need to go to repair station. Moreover, we can use this information to have an historical report of the welding seams that are having issues or not, and then giving feedback to the manufacturing line. So we can update and solve the problem in that robot which is causing this wrong welding, or maybe adjusting the temperature or all these kind of things. Okay. So I went through this presentation. Uh, it took us some 40 minutes. So now we have time for the Q&A session. So you can use the chat box. I will also comment if there are no more questions. I will comment some from the topics discussed this morning. I can see one interesting question from the chat. So it says, what is the accuracy of the measurements? We have two systems, the inline and the offline. In the inline, we are going up to 23 micron with a resolution of 220 micron. On the offline system, by the way, we are going to 40 micron in accuracy with a resolution of 200 micron. Okay, so we can say that we are always sub-millimeter with high degree of accuracy and resolution. Okay, before on the other session, some people was asking about the install base of ABB. So we have install base of offline and inline in Europe, in US, and in Asia. An important point here to highlight is that we have demo cells of offline inspection. Sorry, we have the complete standard cells. We have in Mexico, we have in Canada. Uh, I don't know if we have in US nowadays. We have in India, we have in Czech, we have in China for sure, and maybe and in Spain, of course. So we have these demo cells which are available for customer testing. You can bring there your part, testing and validating the measurements according to your standard regulations. Exactly the same we can do with the inline. So in that case, nowadays we have the inline just in Spain for testing. You can ship your parts. We can check a number of features. We can discuss, and also we are also open to use Robot Studio for the time simulation. So we are putting all these resources to our customers to do testing and to make sure that what we are offering will work on the right way. Regarding references, someone was asking about if they were auto, tier one, if of course, that due to confidentiality issues, we will not disclose the number of the customers, but we have auto for passenger vehicles, we have auto for trucks, We are working with tier one. We are working with some giant industries. And some funny facts. In fact, in the past, this sensor was used to scan some paints in some Spanish museums. So we were going to the level to be possible to check how the brush was painting this paint. Okay, so more questions on the chat. Anyone has an additional question here? Anyone? No? Let's see. Yes, there's one topic that I have to mention. At the end of the session, we will show a QR code where you will be able to to this is the QR code. So by scanning that, you can give your feedback and say if you were finding that interesting or not. Additionally to that, I want to mention that I'm fully available. One interesting thing, thanks to the social media, after the previous session, I was connected to a guy through LinkedIn. So my name is Tony Roda. I'm located in Barcelona. Tony Roda. My email address is tony.roda. Sorry, tony.roda@es.abb.com. So uh, you can contact me at any time. I will be more than happy to answer your questions. So LinkedIn, the easiest way, I would say. Second, ABB email address. It's quite easy also for contacting, for reaching me out. In any case, you can contact your local ABB local team in Mexico, in Canada, and US to provide you additional information. So I'd say that's all. So I'm really happy to participate in this in this breakout session. Again, any question, please contact your local ABB team. You can reach me on LinkedIn or through my email. And thank you very much, guys, for your time. It was my pleasure, and I hope seeing you soon. Thank you very much. Take care.